A survey in the New York Times Almanac finds that the mean commute time is 25.4 for the 15 largest cities. So the mean is 25.4. So the mean is 25.4. So mu equals 25.4. The Chamber of Commerce in a city feels that the commute time is less. So it feels like the mean is less than 25.4 and wants to publicize this fact. The mean for 25 commuters, so they surveyed 25 commuters, so N is 25. The mean for those 25 commuters is 22.3. So the 22.3 is your X bar, it's your sample mean. With a standard deviation, so again, this standard deviation is referring to the sample of 25, so the standard deviation is 5.3. At alpha equal 0.10, is the city's commute time significantly less than the mean commute time for the 15 largest cities? So state the null. The null always has an equal sign, so equals 25.4, so it's going to be this one. The alternative is less than 25.4. So less than 25.4 will be this one. State the p-value. So here we're going to use StatCrunch. So I'm going to write down our data. So we have our null is equal to 25.4. Our alternative is that it's less than 25.4. Our N is 25, that's our sample size. X bar is the sample mean, which is 22.3. S is our sample standard deviation, 5.3. And then alpha equals 0.10. So we use StatCrunch. And when we're at StatCrunch, we go to Stat. Now, which test are we going to use? Do we know our population standard deviation? No. We only have our sample standard deviation. So since we don't have our population standard deviation, we're doing a T-stat, one sample with summary. We don't have a bunch of data, we have a summary. The summary is that the sample average is 22.3. So we have a summary and only one sample. We didn't talk to a group of 25 and then another group of 25. We just talked to 25 commuters at one time. So it's T-stats, one sample with summary. The sample mean is 22.3. The sample standard deviation is 5.3. And the sample size is 25, and the hypothesis is equal to 25.4 and less than 25.4, and then we compute. And so I'm going to write this all down. The mean is mu, the sample mean 22.3, I already have that written down. Standard error, so our SE is 1.06. Our degrees of freedom is 24. Our T-stat is negative 2.92. And our p-value is 0.0037. Okay, so back to this, since you didn't know your sigma, this was unknown. That's why we did a T-stat. And when we did it in StatCrunch, it gave us that the standard error is 1.06 and the degrees of freedom is 24. And the reason for that is n minus 1. So 25 minus 1 gives you 24. Our T-stat is negative 2.92 and our p-value is 0.0037. So the p-value is 0.0037. Our alpha is 0.10. And what is your decision? So there's two decisions. If the p-value is low, the null must go. And the second option is if the p-value is high, the null must fly. And this comes from your book. It helps you remember. So if the null must go, that's really meaning that you're rejecting the null, rejecting HO. And if the null must fly, that means it's good. It's good to go. So we're failing to reject or do not reject the null. So what is your decision? Okay, so what determines if a p-value is low or high? Your significance level, your alpha. So is 0.0037, when you compare it to 0.10, is that low or high? And it's low. So if p-value is low, the null must go, which means we reject it. So we're going to reject the null. When you reject the null, that means that there's sufficient evidence to suggest that the alternative is true. So if you look at this, they think the status quo says that the mean commute time is 25.4, but the Chamber of Commerce thinks that the commute time is a lot less. Now, what you do to prove that it's less is you run a sample, and it does look like it's less, but is it significant? Is this low enough to prove that, yes, the population's mean commute time is less than 25.4? And actually, you can't prove anything, but if you reject the null, if you're rejecting this, you're saying that there is sufficient evidence to prove that the mean commute time is less than 25.4. So that's what we're saying here. So if you reject the null, then there is sufficient evidence to conclude that the mean time is less than 25.4. And then some more background information on this if you wanted to know. So I'll do it in a different color because this is not required because that was the end of the question. But some more background information is if you're using a t-distribution, your mean goes in the middle, 25.4. And your standard error, which is sigma over square root n, but we don't know sigma. That's why we're using a t-distribution. So s over square root n, which gave us 5.3 over square root 25. When you put that in your calculator, 5.3 divided by square root 25 gives us 1.06. That's how we got this. And when you use that, 25.4 plus 1.06, that gives you 26.46. Then you add another 1.06, you get 27.52. And then this is 28.58. This is 24.34, and how I did this is I subtracted 1.06, our standard error, and then another subtract 1.06, I get 23.28, and this is 22.22. So this is 0, the mean's at the middle. This is 1 standard error above, 2 standard errors above, 3 standard errors above. This is -1, 1 standard error below, 2 standard errors below, 3 standard errors below. And so what you're looking at is ours for our sample was 22.3. 22.3 fits right in here, right? 22.3 is in between 23 and 22. And it is between -2 and -3 because our t-stat is -2.92. So that is like -2.92 standard errors below the mean. So if the null is true, and whenever you take a sample, there's always going to be sampling variability, but if the null is true, there is a chance, a 0.37, like if you move this over, a 0.37% chance of getting this value, the 22.3 or more extreme. So it's possible, but it's very unlikely that the mean is actually 25.4. It's more likely that the mean is actually, the population mean is less than 25.4, which is why we're getting a sample mean of 22.3. And so that is why we're rejecting the null and we're favoring the alternative, which shows that there's evidence to suggest that the population mean time is less than 25.4.